Today we'll talk about two extremes. One is microscopic balance, the other is macroscopic balance. The pronunciations of them are very similar, but they are just the extreme, the opposite of the others. First topic is microscopic balance. Last class we have talked about thermodynamics, 3 laws of thermodynamics. Then can we apply the law of thermodynamics to system analysis? Yes, sometimes. For example, we can apply the laws of thermodynamics to analysis of internal combustion engine cycles. You may remember the cycles like Carnot, Otto, Diesel, and so forth in your thermodynamic class of your undergraduate age. Can you remember? Yep, you may remember the TS diagram, but the law of thermodynamics cannot apply directly in most cases. Why? The law assumes the state variable have no spatial distribution, 3-dimensional distribution. The laws are talking about the states, not the dynamics. Dynamics means time dependence. Okay? So we cannot see the time dependence. So we need to extend the laws so that the state variables are functions of time and space. So we usually call them governing equations. Governing equations are usually expressed in differential forms. Consider this small area. We have area here, and we have flow. The flow is going through the area. The velocity is v, and the density is rho. And what is mass input into this space in kilogram per sec? So the mass input is equal to flux times area. Mass input is, as we know, mass flow rate, kilogram per sec. A is just the area. And the flux is m dot divided by area. That means flux is kilogram per sec per square meter is equal to kilogram per cubic meters times meter per sec. That means rho v, and the rho v is the flux. Flux is, as we know, the mass flow rate per sec per area. Okay, so m dot is equal to F times A. In other words, rho VA. Rho VA is the mass flux into the area. It's very simple. If we can generalize the relation, flux in a flow, flux of phi can be given by this equation. Velocity times phi prime. Phi prime is phi divided volume. So this slide is not in your manual. Sorry, I added this manual, this slide today. So mass flux V is V times mass per volume. That means V times rho, or rho V. And momentum flux, the flux of momentum is V times rho V, so rho V square. And the mechanical energy flux is V times rho v square divided by 2. So so the mechanical energy flux is proportional to v cube. Okay, it's very straightforward. Consider the big wind turbine. We have a wind turbine here. And there is wind in a velocity v. So the energy input to this wind turbine is proportional to V23, not V square. Okay? So the energy input to the wind turbine is increase rapidly with V, because the dependence is V23. Consider now 2D flow. What is the flow into the area? We have a scale area, and the base is delta x, the height is delta z, and here we have a flow. The velocity is v, meter per sec, not milligram per sec. Meter per sec, density is rho. So we can apply the same principle. So v is vector. So consider the flux into this area and into this side. So the flux into the rectangle is the sum of flux to this side plus flux to this side, right? So if we estimate the flux to this side, we take the x component of the velocity. So the flux on this side is delta z, it's kind of area, times rho v x component of the velocity vector, right? The same principle is applied to fz and the z component into the area. Consider the 2D flow gain. What is the mass accumulation in the area? Now we consider the mass accumulation within the rectangle. So in this case, the flux on this side is delta z, area times rho vx, as we just seen, and the flux on the other side is rho f is delta z, rho vx at the position x times delta x and z. What I mean is the flux into this area is not the same for the both surfaces, because there is some change in density and velocity. Okay, the density here is rho xz, and the velocity is rho vx x comma z. The density on this side is is a function of x plus delta z. So the accumulation is the area times the mass per area, and the flux change. I mean the area, the mass accumulation is proportional to input minus output. I think this is the general approach you've learned in your undergraduate school. Usually we consider a cube. Base is delta x, delta y, height is delta z. And we consider the flux into the cube in three directions: z, x, y, and z. So only consider the x direction. So the flow rate, the flux is rho Vx kilogram per square meter per sec. Sorry, I missed this time. Kilogram per square meter per second. And the area is delta z times delta y. Right? So the mass flux on this surface is delta y delta z rho Vx minus the mass flow rate on the opposite side is rho Vx x plus delta x, and delta x delta y delta z times rho is the total mass within the cube. So this term is mass change within the cube. This is the one of the approach, or you can take the material volume approach. Okay, you can understand the meaning of a material derivative. The derivation is maybe more simple, but the same principle holds for both cases. Yep.
Did we assume rho is constant?
No. I mean that rho is also a function of x, and rho is a function of rho x. The exactly correct expression for the second term is rho x times delta x z v x plus delta x plus g. Okay. I omit the x plus delta x for the space.
And isn't the rho about space and time?
Absolutely. Density. Consider the density in this room. I'm talking, and the density is changing, and it is the propagation of sound. So density is function of time and space.
And we need t parameter over there.
Right. Yeah, it may be more complete form. Anyway, what is important is that there is some difference between input and output.
How about velocity?
Yeah, the same for density. Yeah, density and velocity are dependent on time, x, y, z position. Now you may forget about the detailed procedure. What you should remember is that this equation. Okay, this equation is called that throughout the mathematical form. If delta x, delta z, and delta y are small, there we can express these equations into differential equations. This is the first form, and this term can be written in delta dot product of rho v, divergence of rho v. So this is the general form, and we call this equation cannoniere, not continuity, cannoniere. The accent is on the first vowel. Is equation of cannoniere.
So we didn't assume that rho is constant, right?
Yeah, this is the general form. Rho is function of time and position. I'm sure now you can recall all the memories. This is the general form of cannoniere. For incompressible flow, incompressible means rho is constant. Rho is constant. Then this term vanishes, and rho can get out of the divergence. So divergence of v, divergence of the velocity is equal to 0, as the canonical equation for an incompressible steady flow. So you may be familiar with this form. Conservation of momentum is if we follow the same approach as in conservation of mass, we can derive this equation. So rho dv divided by dt is equal to minus pressure gradient minus stress tensor. What is that? Tau, stress tensor. Stress tensor plus rho z, and this term is called this operator is called material derivative. dt d is equal to round t round plus v dot gradient. Okay, so this is it your first time to hear about material derivative? No, surely no. If you open your fluid mechanics handbook of your undergraduate age, there should be some explanation about material derivative. Material derivative. What is material derivative? Material derivative is to consider the change of some property when the observer is moving with the flow velocity. So this is the conservation of momentum, or we usually call it equation of motion. So this is the general form of equation of motion. And for Newtonian fluid, the stress tensor is proportional to the velocity gradient. Then this equation, in this case, tau, the stress tensor, is not defined. But we can relate the stress tensor with the velocity. So we have this form. So I'm sure you are familiar with this equation. And for invested is the viscosity is 0. For invested flow, this term vanishes, and this equation is called Euler equation. For steady state case, we can observe this equation. Sometimes it is called Bernoulli equation. We'll revisit this equation when we deal with the macroscopic balance. Now we move to conservation of energy. So we need to define the energy flux. So we assume we take an empirical law. The empirical law is energy flux is proportional to temperature gradient. You agree to this equation? So the proportional constant is called conductivity, right? And we know intuitively that the flux of energy is in the opposite direction of temperature gradient. So Qx, heat flux in x direction, is equal to minus K times gradient of temperature. So in this example, we have the temperature profile in terms of position. So we have a gradient here, dt dx at x1. Then since the slope is positive, the heat flow is negative, and the heat flow is from this to this. Okay. So temperature is like the kind of the internal energy. So we can consider potential energy. It's just the physical slope. If we put the ball here, the ball will roll down the slope. This is the one-dimensional form. We can generalize this to three-dimensional case. So Q, the heat flux vector, is equal to minus Kx times gradient T, temperature gradient. And the Kx, the conductivity, can be a function of space. Assume that there is no heat source or sink within the medium, and the steady state, some terms in the previous equation vanish, and we get this equation. In mathematical terminology, this equation is called Poisson equation. Am I right? Yeah. So delta square time should be 0. There is consider the assumption that there is no heat source or sink within the medium. Then when can you find a heat source or sink within the medium? When is this assumption not valid? No idea? We assume that there is no heat source within the medium. Then when can you find that there is a heat source? Every fluid, every flow has heat source. Am I right? Think about viscous dissipation. What is viscous dissipation? Will, what is viscous dissipation? We have green tea here, and we mix it by shaking it. Then we can observe flow, but this flow will stop within a minute. Why? Because viscosity try to stop the motion. Okay, the fluid is dense, viscous, so the viscosity tries to stop the motion. Then actually we have energy here, the moving fluid here, but it stops. Then where goes the energy? The mechanical energy. Yeah, it was converted into heat. Okay, the process from motion to heat is called the viscous dissipation. Okay. So, but temperature change due to the viscous dissipation is very small. So you usually neglect the viscous dissipation. But when you consider chemical reaction, that some molecule is converted to other molecules, that there will be big change within the fluid. In that case, the heat source is a big issue. In that case, we cannot neglect. So this equation, we can apply this equation to very simple, simplified cases. Conservation energy. To derive a general equation for conservation energy, we should consider three forms of energy because it can transform to the other. So in this case, internal energy, potential energy, kinetic energy. Can you remember the internal potential kinetic energy we've talked about last class? Yeah, so the general form is the change in internal potential and kinetic energy is equal to heat conduction and the energy input through the surface times the viscous dissipation. Okay? But this equation is not useful in terms of engineering application. Why? we can measure velocity, okay? We can measure pressure. Can you measure kinetic energy? How about this? Can you measure the kinetic energy of an object or a fluid?
You can infer from the velocity and mass.
Right. We should know velocity and mass. Can you measure the potential energy? If you know the height from a reference point, can you measure the internal energy? Kinetic energy is okay. Mechanical energy is okay. And how about internal energy? If we know the pressure and temperature, we can estimate internal energy, because internal energy is a function of pressure and temperature. If we know the two independent variable, pressure, temperature, or pressure volume, we can estimate their internal energy. So energy is, what I mean is energy are a second derivative of what you can measure directly. We can measure only pressure, temperature, mass, velocity. Can you measure velocity? Maybe or maybe not. Okay, sometimes these the measurement can be the second derivative of our first the direct measurement. So in this equation is not useful because we cannot measure these variables directly. So we substitute the expression for the internal energy in terms of a measurable property. In this case, internal energy is substituted by a function of pressure and temperature. I recommend you a text written by Bird, Stewart, and Lightfoot. If you open the chapter 10 of the textbook, you will find the detailed procedure. So this equation is expressed in terms of measurable properties. So we convert the change in energy into change in temperature. So this equation is useful. We need further simplification. We can simplify further if the situation is more simple. If we assume linear model for Q and tau for the stress tensor, the governing equation is simplified to this equation. For either gas, to this equation, constant pressure, fluid or solid, this equation. You may be familiar with this equation. Rho Cp times temperature change is equal to K times delta squared temperature. What I wanted to stress is that this equation is just approximation. We needed to three or four assumptions to get this equation. This equation is only applicable to constant pressure fluid or solid. So for your homework, fortunately, the membrane is solid. There is no fluid. So if you solve this equation, you can estimate the heat flux. And in your case, the heat flux is a steady state. So what you should solve is just K delta square T is equal to 0. When you deal with some complex case, you should return to this equation. I'm kind of venting from high pressure vessels. You should consider this equation. In that case, consider this case. We have a pressure vessel, and assume that we are trying to carry a high pressure natural gas. We call it CNG, compressed natural gas. CNG carrier requires a pressure vessel. So we have a pressure vessel. Assume that the original pressure is 230 bar, and there is a leak. Assume that. Then, in order to solve this equation, you should consider. In order to solve this situation, you should consider this equation, and because the internal pressure is changing, so density will change and time dependent. Let's get back to our class, and the topic of this class is macroscopic balance. In the former class, we learned about microscopic balance, but frequently we are in the opposite case, the opposite extreme. Usually we deal with a system which consists of subsystems or components. And we have no interest in the internal details of the components or subsystems. And we want to know the overall features of the component with boundary conditions. So it's close to the real world problem. So overall features, I mean the power consumption, heat transfer rate, heat capacity, and so forth. The boundary condition would be imposed on pressure, temperature, and mass flow rate. So is there any way to describe the property conservations, like the conservation of properties for microscopic world? That is, the answer is macroscopic balance. So we will take a black box approach to the macroscopic balances. The target system can be small or large. It can be a part of compress, or compress itself, or compression unit, or a big plant. For example, the FPSO, the representative offshore installations, contain about 15,000 valves, hundreds of pumps, tons of compressors. It's impossible to describe all of them in terms of a microscopic balance. So the macroscopic balance is very important. The vendors, the expert will take care of the detail. I mean the the compressor manufacturer will analyze their compressor in terms of microscopic balance, but the system engineer should analyze the plant in terms of microscopic balance. Describe all the details based on the microscopic balance is possible, surely possible, to describe the every detail of the parts, but it is not effective. It is not useful. So sometimes it is effective to think in a large scale sense. So that is black box approach. Macroscopic balance, as I explained, is a black box approach, and we consider balances over system. So the system is the black box here, and we concentrate on the boundaries, input and output streams, and overall work done by the system, and overall heat transfer into the system. That is the philosophy of microscopic balance. Consider this simple system. Water is pumped into the pump, and the pump raises the pressure and feeds the water into the heat exchanger, and the heater vaporizes the water and generates steam. In other words, the heater is just a boiler, and there is a steam turbine, and the steam turbine, the high pressure steam drives the steam turbine, and the steam turbine will generate. It's the simplified version of steam turbine generation system, and if we connect generator with the steam turbine, the generator will generate electricity. Okay. In this case, we need heat addition to the heater and boiler, and the turbine will generate work, WT, and we need to supply work to the pump, electric power to drive the pump. So by the definition of the work, by the convention of the sign of the work, the work input is minus and the work output is plus. The total work would be equal to WT minus WP. Is it clear with you? Next, we neglect the inner structure of the system. In macroscopic approach, we consider the system as a black box, and we concentrate input stream 1 and output stream 2, and overall work W and overall heat transfer Q. So we just concede the boundary. Wow. So we can apply the same principles of mass conservation to this system. In the microscopic balance, we consider the small volume. In this case, we just consider the big black box and consider the input and output. So the mass change within the system is just mass input minus mass output. If you know the density, velocity, and the surface in the input and output is just rho 1 V1 S1 minus rho 2 V2 S2. For notational convention, we define delta. Delta phi is just the delta at outnit minus delta at init. So outnit minus init. It's just convention like the sign convention for work. So the material mass change within the system is minus delta W. W is just mass flow rate. So minus mass flow rate change. The output, the minus sign is because of the sign convention for the operator delta. Operator delta is defined by output minus input. You may remember the conservation of mass for a three-dimensional case. For the microscopic balance, we consider this small volume, and in this example, we just consider the flux in this direction, and flux. This is the term for flux in, and the mass flux out. So what I mean is the principle is the same. We just consider the target volume, target space is just increased for the macroscopic balance. This is the mechanical energy balance for in terms of a macroscopic sense. The system energy, the kinetic energy plus potential energy plus internal energy. Internal energy for macroscopic system is just Helmholtz free energy. Please open your thermodynamic handbook. It is equal to the change in kinetic energy, potential energy, and the Gibbs free energy times mass flow rate minus work minus EV. EV is a frictional loss. These all terms, the first term is defined for the boundary, just the position at input and output. And this term is about the whole system. Work is done on this by the system, not on the input or output stream. Can you understand? This term, first term, is for the boundary. This term is for the bulk, the system. Work here is for the work done by the system, not on their boundary. So I recommend you open the book of textbook written by Birdstewart and Lightfoot. Any question? No? If we consider steady state, we usually interested in steady state operation because steady state operation gives us the basic information for equipment design. So this equation is simplified to this form, and this form is called Bernoulli equation. Bernoulli equation. You may be familiar with this form, okay? And that means kinetic energy change times potential energy, not change, difference, kinetic energy difference between input and output plus potential energy difference plus the pressure difference between input and output plus work done by the system plus EV is equal to 0. If if you define the, consider this case. Here we consider the Gibbs free energy, so you can change it another form. In this equation, the Gibbs free energy is changed to enthalpy. The enthalpy is convenient energy. It can be usually defined by the temperature change times Cp. Constant pressure, heat capacity. Then the equation is converted to this form. So that means that's why we check the enthalpy change when we deal with a big system. Okay, enthalpy can be estimated easily by measuring the pressure and temperature, and that means this expression is easy for us, for mankind. Okay, because mankind can easily measure the pressure and temperature and constant pressure, heat capacity. Imagine the situation. You need to measure the specific heat. There are two kinds of specific heat. One is constant pressure, specific heat. The other is constant volume. Usually, constant pressure, specific heat is more convenient to measure. Under the atmospheric pressure, we just measure the temperature difference after we apply some heat. Then we can estimate the specific heat, constant pressure specific heat, because the pressure is 1 bar here. So what I mean is this equation is a useful form for engineering. When we consider more complicated situations like the CNG tank, okay, in this case, all the variables change with time, and internal pressure will change. So in that case, we should use this equation. This equation is valid for the case where the kinetic and the potential energy are negligible. And in most cases, kinetic energy and potential energy are small compared with the energy itself. What I mean is, what is the potential energy for the gas within the container for the CNG tank? Potential energy difference for this tank would be rho ZH, right? I will compare the gas here and the gas near the ceiling, gas near the top and the gas near the bottom. Maybe the potential energy difference would be rho ZH. Because the gas density is very small, we can neglect the the potential energy. How about the kinetic energy? When this velocity is small, we can neglect the kinetic energy. What I mean is consider the heat exchanger. We have a heat exchanger, and the inlet temperature is for the system we are considering maybe 30 Celsius. Maybe output this in our example we applied some heat and vaporized the water, and it will become steam. Maybe the steam temperature would be 300 Celsius. Because there is some phase change, the outlet velocity would be increased. What I mean is the incoming flow velocity would be 3.0 meter per sec, and outlet velocity can be around 30 meter per sec. So the kinetic energy for the outlet stream is much higher than the incoming fluid. But compared with the enthalpy of the outlet stream, and the enthalpy of the steam, this kinetic energy is just chicken feed, less than 1/1000th, less than 0.1%. So in this case, kinetic energy is not comparable to the enthalpy itself. Can you understand? Okay, let me explain this. In order to generate the steam, we apply the energy. Okay? Assume that it would be 1000 joule per sec. This energy is the source to increase the enthalpy and velocity. What I mean is this energy is used to increase the temperature and the velocity. In other words, enthalpy change, internal energy, or the kinetic energy. Then how much? Maybe 1 joule is used to increase the velocity, and 999 joule is used to increase the temperature. Understand? In this case, but in this case, we consider the internal pressure is 230, and consider the velocity from this leak. We have a small leak, maybe 1 centimeter hole. Then what is the velocity? If the container internal pressure 230, 1 meter per sec, 2 meter per sec. This is a typical case of a choked flow, and the choked flow velocity is the sonic velocity of the internal pressure. What is the sonic velocity for 1 atm? 340 meter per sec, right? If the pressure is increased to 230, maybe the sonic velocity is far above 500 meter per sec. So in this case, the leaking velocity would be greater than 500 meter per sec. In that case, we cannot neglect the kinetic term. So we cannot apply this equation. Then which equation we should use? If you open the book, the textbook, there are several examples. Okay, so there are some good explanation why we should use this equation. So please read the textbook. The textbook is written nearly 50 years ago, but I think it is the most excellent, not one of, just the most excellent book I've ever found.